Welcome back to my channel. So we continue the next part 6.4 thin lens formula, still under the same chapter 6 light and optic. Okay, in my previous video I have discussed about two types of lenses, convex lens and concave lens, and also I have discussed about terms object distance U, image distance V, and focal length F for a lens. So the three variables here can be related by this equation known as lens equation. So 1 over F equals 1 over U plus 1 over V. The value of 1 over F is also known as power of the lens. So defined power of the lens is ability of the lens to focus light. So we have P equals 1 over focal length in meter. So we get the unit is diopter. So when we use this formula to calculate, so you need to make sure you know about the sign that you need to use in this case. For example, the focal length. If the lens used is convex lens, so the value of focal length is always positive. If the lens used is concave lens, the value of focal length is always negative. As we discussed before, the focal point of the concave lens is virtual. So that's why the value of F is negative. You need to put the negative sign in the calculation. Image distance V, for real image, the value of V is positive. For virtual image, the value of V is negative. So same thing for the power. For the convex lens, the power is positive. For concave lens, the power is negative. So because when you use this formula lens equation, you need to take this into account. If not, you will get different answer or wrong answer. Okay, now you refer to your textbook, experiment 6.3. So this experiment is to study relationship between object distance U and image distance V for convex lens to determine the focal length of thin lens using lens formula. Meaning we want to produce lens equation by carrying out this experiment. Okay, the inference for this activity is image distance influenced by object distance. Hypothesis: when the object distance increases, the image distance decreases. Okay, now let's look at the variable involved here. Manipulated variable is object distance U, corresponding variable image distance V, constant variable focal length F. Don't write lens, convex lens. You always write physical quantity here, focal length F or power of lens, P. Apparatus required here, convex lens, lens holder, 6-volt bulb, wooden block, power supply, cardboard with a small triangular shaped hole, white screen and meter rows. Okay, you can carry out this activity in the lab. So you can change the focal length of the lens, depends on what you have in your lab. Okay, so now you can observe this video to understand better this experiment 6.3. So in this experiment, use a focal length of 20 cm. So material required, so we have lens holder, convex lens, focal length 20 cm, screen, candle, so the flame of the candle will become an object, okay, what we do is, as we know that the focal length the focal length of the lens in order to check whether we can get the accurate value or not by experiment. Okay, this one is 20 cm, so we can just mark or no need to mark also can. You can put f1 is 20 cm, 40 cm, and so on. Okay, so now for this activity, for let's say we have 5 value of u. Okay, you can start with u equals to 21, for example, or 20, 25, 30, 35, 40, and so on until you get 5 value. Okay, so what you do, you just for example, you place the lens from the candle at distance, let's say 25 cm. And then what you do, you adjust the screen until you get a sharp image form on the screen. And then you measure the distance between the center of the lens and the screen. That one will become the image distance. So you can repeat the experiment until you get 5 set of data. Okay, maybe initially you use 25, the next one is 30, 35, 40, 45, and so on. Okay, until you can get 5 set of data. So you can observe here the image form. So you need to adjust the screen until you get a sharp image. Okay. Normally in this activity, we use the range of u which can produce a real image. Okay, so normally to produce real image, the object distance must be greater than the focal length of the lens. Okay, so you record all the readings in the table for you to plot a graph. From the graph, we can get a lens equation and also focal length. Okay, so you can see here again, if you want to continue, you can search the video in the internet for more information on this. Okay. Okay, now let's say we have this table of data. So from the activity, you have recorded 5 set of data. Okay, this is only a sample of answer. So you have recorded for the value of u and v. So you have this value. And then you calculate for 1 over u and 1 over v. Okay, from the value of 1 over u and 1 over v, you plot a graph of 1 over v against 1 over u. So you get a graph like this, which shows that 1 over v is decreasing linearly with 1 over u. So from this graph, we can determine the lens equation and also the focal length of the lens used. So from this graph, this is a straight line graph. So the formula generally is y equals to mx plus c. They put negative here because this one is the negative gradient. So the gradient equals to m equals negative 1. Okay, so 1 over v, this is y. Negative 1 is m. 1 over u is x. 1 over f, actually the intercept of the graph at y-axis. Okay, so because only c, c is 1 over f. So from the value here, you can calculate what is f. Okay, then from here, we can get lens formula as 1 divided by f equals to 1 divided by u plus 1 divided by v. So this one is known as lens equation. So what we can say about the focal length? So from the graph here, we get c equals to 1 over f, meaning 1 over f equals to intercept of the graph 1 over v against 1 over u, and the gradient m equals to negative 1. So you can calculate f equals to 1 divided by intercept of the graph 1 over v against 1 over u. Thus, we have proved that the lens equation we can get throughout this experiment, and also the focal length can be determined by using this experiment. Let's say you don't know the focal length of the lens, so you can try to carry out this activity, plot a graph, and then you can find the intercept of the graph, then calculate for focal length of the lens. Okay, now we look at some of the problem solving using lens equation. So you must be careful when you read through the question whether this one is convex lens or concave lens. So a thin convex lens has focal length of 12 cm. Determine characteristic of the position of the images form and linear magnification when the object distance is 18 cm, 4 cm. Okay, part A, given focal length is 12 cm. A, object placed here, meaning u equals to 18 cm. From length equation, so what you do, you substitute the value of u and f, so you get v. You get v equals to positive 36 cm. So you get the value of v positive, meaning the image is real. Then calculate linear magnification. M equals to image distance divided by object distance. Image distance is 36, object distance 18, thus 36 divided 18, you get 2. Meaning the image is 2 times bigger than the object. So from the value that you calculate here, actually you can state the characteristic of image. So from here we get image is real, if real is always inverted, and magnified. If you look at the magnification here. Okay, so image is located 36 cm from the lens and on the opposite side of the object. So image is magnified 2 times. So meaning the lens equation really help you to get the characteristic of image. Okay, B, let's say u given is 4 cm. So you calculate from here, you get v is negative 6. The value of v negative meaning virtual image. So you calculate for linear magnification, mv divided by u. So when you calculate for linear magnification, no need to put the negative sign because this one is just to calculate how many times bigger. Okay, so v is 6 divided by 4, so you get 1.5. So what you can say about the image is virtual. Once virtual is always upright. So virtual, upright, magnified. Because the value of m is more than 1. Okay, if m equals to 1, same size. If m less than 1 is diminished. Okay, so what we can say about the image is located 6 cm from the lens and on the same side as the object. Image is magnified 1.5 times. Okay, so you need to be careful with the sign. Okay, example 2. Object height 9 cm placed 60 cm from a concave lens. You can highlight in this one so that you won't get confused later. With a focal length of 30 cm, determine the position and size of the image form. State the characteristic of the image form. So u equals to 60 cm. F equals to negative. Why negative? Because here is concave. So the focal length is negative. Straight away you write down the negative sign. So using the thin lens formula, you substitute the value of u and f. So remember the negative sign must be added in. And then finally you get v here, negative 20 centimeter. So meaning the image is virtual. Linear magnification m is height of image divided by height of object, also equals to image distance divided by object distance. So we are going to use the two formula at the same time because the information given here is about height of image, height of object, object distance, and image distance. So you calculate, you get image, height of image is 3 cm. So the object is 9 cm. So you can see here, image is 3 cm. Okay, so the image is smaller. Okay, so the characteristic is virtual because the v is negative here. Virtual, upright, and diminished. So image is 20 cm from the lens and is on the same side as the object. So image height is 3 cm. Okay. Example 3, figure 6.37 shows straight wire placed along the principal axis of thin convex lens focal length of 12 cm. X and Y are 24 cm and 18 cm respectively. The cricket takes 6 seconds to move from X to Y. Okay. What is the speed of the cricket's image? So this one is a hot question, so relate to the speed. Okay. So solution, we have initial object distance is u1 18 cm and then u2 is 24 cm. So we have for x. Okay, So this one is y, sorry, u1 is for y, u2 is for x. And then the focal point is positive, 12 centimeter. So you calculate for v1 from here. Okay, you substitute the value of f and u1, you calculate for v1. So the image form for object at y. Okay, so it's 36 cm. And then you calculate for v2. You substitute the value of f and the u2 24. Okay, so you get the second image is 24 centimeter. So the distance traveled by the cricket from x to y is 36 minus 24, meaning it traveled a long distance of 12 centimeter. Okay, 12 centimeter. So by using the formula of v equals to s divided by t, the time taken is 6 seconds. So distance travel is 36 minus 24. So divide by 6. Thus get 2 centimeter per second. So this one, be careful. First, you need to identify what formula that you need to use in this question. Okay, last part we discuss about the formative practice 6.4. I think it's better for you all to try first before you check the answer. Okay, number 1, a concave lens with focal length of 25 cm form virtual image of an ant at distance 20 cm from the optical center of the lens. A, what is the original position of the ant? B, draw a ray diagram to show formation of the virtual image of the ant. Okay, number 1A. We want to determine the original position of the ant, meaning the object distance. The ant is the object. Okay, given f equals to negative 25, because this one is concave. V is equals to negative 20, because stated here is virtual. Okay, so you must put the negative sign. Okay, and then use lens equation, you calculate. You substitute the value of f, negative 25, the value of v, negative 20. Then you calculate, you get u equals to 100 cm. Meaning the original position of the ant is 100 centimeter from the lens. Okay. Okay, now the diagram. Draw ray diagram to show the formation of virtual image of the ant. Okay, so for the concave lens, as we know, there's only one characteristic of image, and the object distance does not affect the characteristic of image. So let's say here the position, okay, of the object, and then you draw two rays parallel to principal axis, diverge from F, pass through center straight line. So this is the image that form. Okay, you can mark the distance here. This is 100 centimeter, and then image here is 25 cm. Okay, here is 25. Okay, so you get this diagram as the ray diagram for the answer B. Okay, number 2, a small bulb is at distance of 1.6 meter from the screen, and thin convex lens, focal length 30 cm, is placed between bulb and the screen. Determine two position of the convex lens that can produce a sharp image on the screen. Okay, now I try to solve it mathematically. Maybe you have another method you can try. So given information u plus v, because bulb and the screen, meaning the object and the image, is 160 centimeter. Here is 1.6 meter. So u plus v equals to 160 centimeter, and given focal length is 30 centimeter. So we apply a lens equation, so we can just rearrange. So we get here 1 over f equals to u plus v divided by uv. Substitute the value of f 30, and then u plus v is 160. And then make it uv as the title, so you get uv equals to 4,800 centimeter. So now you have two equations. The first one is u plus v equals to 160. Second equation, uv equals to 4,800 centimeter. So I mark as this one as equation 1 and equation 2. Okay, so what we do next, we want to solve it simultaneously, simultaneous equation. So by using method of substitution, so from 1 we get v equals to 160 minus u. So substitute 1 into 2. So we have u times 160 minus u equals to 4,800. So you just simplify to become one quadratic equation here. Okay, so it becomes u squared minus 160u plus 4,800 equals to 0. And then you factorize that quadratic equation. So you get u equals to 40 cm and 120 cm. So meaning the convex lens is placed either at 40 cm or 120 cm from the bulb in order to produce a sharp image on the screen. Because when produce sharp image on the screen, meaning the image is real. Okay, so we get this answer, two position which can produce sharp image on the screen. Okay, so I think for this part I will stop now. So we have finished 6.4. So you can try to do more exercise on this, get familiar with lens equation, and you can search more videos on this topic, the experiment and activity, so that you can understand better this topic. Okay, that's all for today. Don't forget to subscribe my channel so that you won't miss my next video. Okay, bye.